You. Awesome. So we have the pleasure today to have Sasha Tchekhovskoy from University of Northwestern. So just to introduce him a bit, so Sasha, you did your PhD at Harvard, and then you did a fellowship at Princeton. After that, another fellowship at Berkeley until you arrived at where you are now, so University of Northwestern. So you work on compact objects, including black holes. That will be the topic of today, and in particular about how gas accretes into those objects in accretion disk and how they trigger feedback in the form of jets or radiation, with some of the most amazing simulation that one can see, including magnetic fields, radiative transfer, and general relativity for gravity. So the floor is yours.
Thank you very much, Johan, and thank you very much for the introduction and the opportunity to meet with you virtually. I was secretly hoping that things will improve and I will be able to visit you and say hello to all of you, but maybe next time. So I'm walking my virtual world, which I built in the little bedroom in our apartment in Chicago. I used the setup to teach. I also used a different setup where instead of the green screen, which I have behind me, I have a black screen, and I put a piece of plexiglass in front of me and I can write on it. So it glows and the people can see me through the glass and see what I write. And so that's called the lightboard setup. So if you're interested in using that for your teaching or for remote presentations, both of which would work, let me know. I'm really happy to share everything I learned in the last year and a half when I had to suddenly figure out how to do all this teaching online. So today I'm going to be talking to you about black hole explosions. And so that's the answer of what a black hole can do for you. It can use the outflows it produces to explode whatever you insert it into. And I'll tell you more about all the fun ways that we can simulate that and what we can learn from those simulations. So these are the different explosions the black hole can power. They can explode galaxies where the black hole mass at the center of the galaxy is millions to billions of solar masses. They can be exploding the accretion disks or the binary system through these collimated outflows, which we call the jets. Even more dramatic can be explosions in the case when two neutron stars merge. These can lead to not only gravitational waves, as we will see in a bit, but also to the bright flashes on the sky called the gamma ray bursts. So these are known as short gamma ray burst progenitors. And we can also produce black holes during the core collapse of massive stars. And those are known as long gamma ray bursts because the jets that drill the hole through the star and emerge, they last for longer. They can last many seconds or even minutes. These are two classes of black holes, the big ones and the small ones. Recently, there is evidence now emerging for, and not surprisingly, a class of black holes called intermediate black holes that spans the gap between the 100,000 and maybe a few tens of solar masses. Excuse me. I apologize. I just had my breakfast. It's pretty early here. It's 8 a.m. So I was like breakfast, and then my food is still in the throat. These intermediate mass black holes are really thrilling and exciting because they could be seeds for supermassive black hole growth. They could also be the power behind ultraluminous X-ray sources, these enigmatic sources that produce way too much X-ray emission for their size. And we'll return back to them. There are a lot of exciting mysteries about them as well. And you can see that in all of these sources, except perhaps this one, I just didn't show this, all of them produces collimated outflows or jets. I want to be fair to all the other sources, which actually do have a physical surface, unlike the black holes. They can produce the jets as well. So, for instance, in the case of neutron stars and white dwarfs or regular stars, we actually can observe jets in all of these cases, except that this is the only observation of a jet that I show here. Everything else is artist depictions. And this is a really active field with lots of new discoveries happening, once a year or maybe even more frequently. So for instance, we of course all heard about the detection of gravitational waves from colliding black holes. And I like to illustrate this discovery with Malevich's black square painting that I show here. I in fact argue that Malevich predicted the gravitational waves by painting this piece of art because we didn't see anything. We only heard gravitational waves. So I contend that he beat Einstein to the theory of general relativity. Of course, I'm joking. There is also another really cool discovery that happened shortly thereafter, the discovery of gravitational waves from the collision of neutron stars. And that was even more thrilling because we actually saw the products of this explosion, because neutron stars, they contain matter, and this matter is neutron rich, and when it's ejected, it decays radioactively. And so we basically are watching the nuclear explosion in space and the products of this explosion. Really important. This is referred to as a kilonova emission. And also the sources are the primary contenders for the production of heavy nuclei and enrichment of the universe with heavy nuclei. The exploding stars sometimes throw us twists, and some of them produce explosions that last not a couple of minutes as we thought, typical, but a few hours. So how is this possible? And moreover, as the star is exploding, it manages to produce this jet for a few hours as if nothing is happening. And at the same time, we know that some of these stars actually undergo an explosion. We see a bump in the light curve at the late time. So how is it even conceivable that a star, basically its house is burning down, the jet doesn't seem to worry about it at all. It seems to be produced just fine, lasts for hours. And at the same time, in the end, we know that the star actually did explode because we saw that bump. So it's like, I have an analogy of this to this problem when you can inflate a balloon with the air. So you blow in the air into the balloon, and there is a hole in the balloon, actually two holes on the opposite sides, to kind of symbolize the jets, the energy that the jets are stealing from the star. In this case, it will be magnetic energy. In the case of a balloon, it will be, of course, the air pressure that will be released. So here we're releasing the magnetic pressure through these two holes. So we need to fine-tune the rate at which we're blowing the air into the balloon such that the balloon doesn't explode too early, so it lasts for 3 hours, that the air comes out of these holes at a pretty constant rate, and then at the end we explode it. So how does it work? Why does this system live for so long? Why doesn't it explode earlier? So this is really a mystery, and if anybody has any ideas, I'm more than happy to chat about that to you. Another really interesting curveball was thrown to us by what we thought was intermediate black holes, but then it turned out that it wasn't. It turned out that we detected pulsations periodically from a few of such systems, which made it clear that what we thought was maybe intermediate mass black holes of tens or hundreds of thousands of solar masses actually was just a couple of solar mass neutron star. So that shows that we still don't quite understand how to interpret the observations and invert the observations into the underlying physics or the nature of the system, which highlights the importance of carrying out the numerical simulations, much like what I will be showing to you today. And finally, last but not the least, black holes can rip stars apart, as we call them, spaghettify them. If the stars come way too close to the black hole, where the black hole tidal forces overcome the forces of self-gravity keeping the star together. And then the star gets stretched out into a thin strand, and it basically resembles a spaghetti. And so that's why we call them spaghettification. And so in this case, not only can the black hole produce an accretion disk out of the strand when it wraps around the black hole and collides with itself, but it can also produce the jets. So these are really exciting laboratories of astrophysics, of accretion and jets, where the budget of the mass is known. It's basically one solar mass, give or take a factor of few, which by astrophysical standards is spectacular accuracy. And so we can use these astrophysical laboratories for quantitative experiments on black hole accretion and jets. So what I'm going to do now is I'm going to overview the physics of this jet production. It turns out it's nearly the same across all of these sources, including those that have a surface. And I'm happy to talk more about this, of course, as well. And you have world experts here in this virtual room, such as Jean-Pierre. So if after the talk you have more questions, you can also talk to him. He will definitely be a perfect resource for this sorts of physics puzzles. So let me start with the basics. What I'm going to try to address in this talks is I'm going to try to be sort of jet dietologist. I'm going to be interested in what is a healthy jet diet. So how do we need to feed the black hole for the jets to be there and be nice and powerful, in good shape? What sets the power of these jets, and how does it relate to the power of accretion, the rate at which the black hole consumes mass energy at the rate of m dot c squared? What controls the jet collimation? Because this is an important observable. We see that the jets are collimated. So what controls that? And what does it tell us about the environment of the black hole and the physics of the central engine? How does these jets accelerate? Because not only do they collimate into tiny opening angles, they can also move at speeds that are very close to the speed of light, as I will discuss later. Where do they get the mass that the jets carry? And how do they shine? So these are all really big questions, and I won't be able to address all of them, but I will at least try and push the science, hopefully, in the right direction. Also, I will discuss the curious case of jet direction, because it also tells us about something, about the preferred direction in the system. For instance, in this case, this is a 3D rendering over simulation where both the black hole and the disk midplanes were aligned. But what if we consider a more general case? Gas comes from large distances, has no idea which way the black hole midplane is oriented, and so there will be, in general, misalignment between the two. So which way will the jet point in this case? Will it point in the direction perpendicular to the disk midplane or to the black hole midplane? Or maybe there will be no jet at all. And so this, to my great surprise, was not a known, like we didn't know what the answer to this question was. So I will try and address that question. And I will also try and figure out why do some of the jets fall apart if I have the time at the end. And finally, I will try and address an important question of the accuracy of our numerical simulations. Okay, well, it's all good and well. We run all the simulations, we make beautiful movies, but how do we know that the numerical uncertainties introduced by finite discretization and so on of the numerical equations actually not interfere with the physical outputs that the simulations provide, so that the results are independent of the numerics? So there's a lot of things to do, so please buckle up and stay with me and enjoy. So let me start with a few examples of explosions that we actually can see on the sky. So this is a Perseus cluster, and if we look at it in X-rays, we see the here the picture on the left. But if we actually do some sort of image magic on it and sharpen it, you will see that these X-rays reveal the sort of ripples that are propagating away from the central black hole, which could be shocks or sound waves. And you can also see that there are these blobs inflated by the black hole, call them cavities, which probably carry away the energy from the black hole and inject it into the ambient medium. It's probably the jets that are doing this. It's really important to try and understand the sort of interaction between the black hole and the ambient medium, which we also refer to as active galactic nuclei feedback or just black hole feedback. Here's another example of black hole feedback through jets. Here we actually see the jets very well, although there are images of jets in the previous system as well. We can see that there are these jets in the M87 system. This is a black hole that was imaged very recently on the scale of the event horizon. I will talk more about this. There is a cavity inflated by the jets on one end. There is another one on the other end. There are shocks that are produced by the system. So we see more of this sort of explosive nature of black hole interaction with the ambient medium that is mediated by these collimated outflows or jets. And this is perhaps my favorite example of the sort of black hole galaxy connection in the galaxy cluster MS 0735.6. Here you see that the two jets shown in purple actually appear in the places where there is a little blue emission, which shows the thermal emission from the hot X-ray emitting gas. So what we see here is that the jets actually inflate the cavities and displace the gas. So they have to do work in order to inflate those cavities, just like I was doing work when I was inflating the imaginary balloon. That's exactly the same kind of PDV work that the black hole has to do through the jets. And if we compute what this PDV work is and compare it to the entire rotational energy of the supermassive black hole at the very center, we will find that the two are comparable to each other. So it's as if something came to the black hole, stuck a big stick into it to slow it down, took all the rotational energy and dumped it into the ambient medium. And so, spoiler alert, we think that the stick is magnetic fields, and they can be really effective mechanism. They can offer a really effective mechanism at extracting the black hole energy and coupling it to the ambient medium. So what are the ways of quantifying the sort of feedback and connection between black holes and the ambient medium? So one way of doing so is to plot the mass of the central black hole versus the stellar velocity dispersion in the central regions of the galaxy, or the galactic bulge. And what we see here is a tight correlation between the two. You can see the data points. Each of them represents one galaxy. And that's telling us that the growth of the central black hole and of the galaxy are tightly correlated. Is this correlation coming from the feedback that the black holes perform on the galaxy through jets or through radiation? Or could it emerge naturally from coevolution of the galaxy and the black hole both grow at the same time and maybe by the same processes? This is still an open issue. There's another way of looking at the same by plotting the logarithm of the radioluminosity of core plus extended, so core coming from the immediate vicinity of the black hole, extended emission coming from the jets in the radio, and the horizontal axis will be the nuclear B band luminosity, or the optical light coming from the very central regions. The vertical axis typically is associated with the power of the outflows, the jets, and is powered by the synchrotron emission of electrons gyrating on the magnetic field lines, whereas the horizontal axis is typically thought to be a proxy of the amount of gas that the black hole gobbles up per unit time, or the mass accretion rate. So if we were in an ideal and simple world, we would say, okay, well, the horizontal axis tells us the supply of the black hole. And for the same supply, we'd probably expect that the radio emission or the jet power would be about the same. But that's not quite true. So in this case, we see two groups, two tracks of galaxies. One is the upper track, the radio loud track, and the other one is the radio quiet track. And the difference in radioluminosity between these two tracks for the same mass supply, the same optical luminosity, is about 3 orders of magnitude. So what can tell a black hole that it needs to be on the radio loud, the upper or the lower track? Well, the jet power could depend on the mass of the black hole, which is within a factor of a few to 10 is the same between these two populations. Can depend on mass accretion rate, which we think is the same because the optical light is the same. But there could be another or a few more hidden parameters, one of which could be magnetic flux. Maybe these ones, the radio loud ones, have a stronger magnetic flux near the black holes, and so they produce more powerful jets than the radio quiet ones. Maybe the ambient medium is different. And in the case of radio loud galaxies, there is less ambient medium to obstruct the jets, and so the jets can propagate further out and thereby shine out their energy more efficiently, whereas these ones are kind of smothered and can get out, and so we don't see their emission. Or it could be differences in black hole spin. Perhaps these ones have a powerful, rapidly rotating black hole that can power the jet, whereas this one maybe is a wimpy, slowly rotating black hole, and there is not much rotational energy that can be extracted by the magnetic fields. So this actually is still an open question, and there are even arguments put forward that maybe this is a selection effect, because all of these symbols are coming from different surveys, and so they might have their own biases. So this is still an open question. And by the way, this paper, did I put the reference here? Yes, Jean-Pierre is right here on this paper, so definitely talk to him about this if you're interested. So maybe we can take a look at a few of the beautiful images of this galaxy to try and give us some more intuition, because the numerics, the quantitative estimates don't seem to tell us the full story. And these are two of my favorite galaxies. This one is a Cygnus A galaxy with a really powerful jet. You see it's very collimated. The black hole here is around 10 billion solar masses at the center. It produces twin jets propagating in both directions, very, very collimated, ending up in hotspots where the jets hit the ambient medium. And just like the water bouncing off, if I take a garden hose directed at the wall, the water will come out of the garden hose and bounce off the wall. Similar to this, we have these backflows that sort of bounce off the jet fluid off of the ambient medium. So it looks like there is nothing here, but for the jets, it's actually some, something to navigate. And so this is why there is a hotspot where the ambient medium stops the jets and the jets kind of splash sideways and backwards. The picture is qualitatively different in the M87 galaxy. First of all, you see that there is only one jet. The other one seems to not be there. We think that it's happening because this jet is pointing at us, and so its emission is amplified due to the Doppler boosting. This one is Doppler deboosted, so the aliens on the other side of the black hole will see that jet, but won't see this one. And you can see that there is a swoosh at the end on both ends over here and over there that is indicating the jet destruction via the interaction with the ambient medium. But you can see that this jet looks nothing like that jet. This one emits most of its emission at the very ends of the jets at the hotspot, whereas this one is bright throughout and kind of whizzles out at the very end, but not much emission happening over there. And this is known as Phanerophili dichotomy of active galactic nuclei. This one is Phanerophili type 2, and this is type 1 system. And what causes dichotomy is a big open issue. You see that the masses of these, do I show? Yes, in both cases at 10 billion solar masses, the jets are similar, the galaxies are similar. So what is it? Is it the change in the central engine or in the ambient medium that controls this? Or is it something else, perhaps the magnetic field or black hole spin? So also an open question. So far we haven't been doing too well at trying to pin down the physics that creates all this variety of black hole powered systems. So maybe we can try and zoom in at the very center and make a movie, and that will tell us something. We will maybe see, especially if we could make a movie at the scale of the black hole event horizon, that will maybe just tell us what the field strength is and how fast the black hole is spinning, everything we ever wanted. So this is a zoom in from 3,000 light years to just 1 light year. This is a movie with about 20 frames, if I remember right, maybe like 3 weeks apart. And you can see that on this, over this longish time scales, there is pattern moving away from the center. The black hole is hiding somewhere to the left of this bright hotspot, which is called the core. And you can see that stuff is moving away. So what we think is happening is that the jets are produced at the very, very center of the galaxy, very near the event horizon of the supermassive black hole. And they start slow, but then they move further and further out, they accelerate. And they eventually reach Lorentz factors of, in this case, we will see, of around 10-ish, meaning that they move at the speeds which are very close to the speed of light, 99% plus of the speed of light. So let's try and take a look at the image of the black hole. But first, how would we actually be able to see a black hole? Because it's really small on the sky, because although it's massive, it's also very, very far. So it turns out that in order to image the black hole, in order to beat the diffraction limit, we would have to have a telescope the size of the Earth, which of course is completely impractical, although it does look pretty cool. So what the scientists have figured out is that they can scatter radio dishes throughout the globe. And here you can see a bunch of them scattered in Hawaii, United States, Europe, and then Chile, South America, and maybe even on the South Pole. And then if you combine the signals from these telescopes, build an interferometer out of them, and wait until these telescopes rotate because of the rotation of the Earth, each pair of the telescopes will produce this sort of pair of arcs. And as you keep adding more and more systems to the array, you will fill more and more of this Fourier UV space. This basically is not the physical space, but the Fourier transform of an image that we would like to make of the black hole. And so if we can make a inverse Fourier transform to get the image, then we will see something like this. This is the best ever simulation created by the code Interstellar. But we will actually see the real simulations because, of course, this is just drawn by hand. And it's missing a few effects such as the Doppler boost, because it looks more attractive like this. One side we expect moving towards us, the other one away from us, and so one side should be much brighter than the other. So this is the actual image obtained by such an Earth-sized telescope, which is called the Event Horizon Telescope. This is the M87 black hole. So we are looking at the very, very heart, the center here, and the size of the serene is around 10 gravitational radii. And we can actually have a movie of 4 frames, in April 2017. And what you can see is that the black hole itself is this dark spot in the center. This is the region where no light originates from. Just outside of that, there is a ring of light, which is the Einstein ring, which is kind of a lensed image of stuff around the black hole. This is a caustic caused by geometry of the general relativistically curved space-time. So light wraps around the black hole, and that's where it all piles up. So that's where the serene originates. But there are some features that are modified by the actual physics around the black hole. And one of them is that the bottom side is brighter than the top side. That's precisely the Doppler effect that I was telling you about that was missing from the Interstellar movie. And so looking at this image, we can learn 2 things about the black hole. One thing is the size of this image is directly proportional to the black hole mass. So it tells us that the mass of this black hole is 6-ish billion solar masses. This actually resolved the controversy. There were 2 measurements, one using the gas, one using the stars, gas motion and star motions, that were different by a factor of 2. So the 3 billion solar mass measurement turned out to be lower than the actual one. So this settled that controversy. And the other really cool thing that was completely mind-blowing for me when I saw that is that by combining this observation at small scales with the observation of the jets in large scales, we can infer the sense of rotation of the black hole in the sky. If we assume that the jet comes at perpendicular to the black hole midplane, then the rotation has to be like this, because the bottom part has to be coming at us because it's brighter, it's Doppler boosted. And the top part has to be moving away from us because it's de-boosted, it's less bright. And so that means that the black hole and the gas around it rotating in the clockwise direction on the sky, which is the first time I'm aware of that anyone was able to measure, if not the magnitude of the spin, the actual sign of the spin. There are different ways of measuring the magnitude, but this is, as far as I know, this is the most robust way of measuring the sign of the spin. I don't know why we need this, but it's really amazing that we actually can do that. And this is a spectacular measurement. Hopefully in the future, there will be even more exciting results coming from the Event Horizon Telescope, such as, in this case, the polarized image, which contains even more information. Here you see the polarization streaks that indicate which way is the electric field oriented in this image. So I'm going to move on, not going to come back to that. I'm more than happy to talk about the sort of physics that we can do with the black hole event horizon scale images. But I think that you need to go home and eat dinner, and I will need to go and teach in about an hour and a half. So let me go into the physics world of black holes and their jets. So how do black holes manage to produce the jets? Well, let us start with a disco ball that's going to be rotating at the constant angular frequency omega. This disco ball will be very special. It will be highly conductive, which means that if we take a vertical field line and attached by one end of this field line to the disco ball, if we move the surface, then the field line foot point will have to move with the surface. The other end we will attach to the ceiling, which represents the ambient medium, ambient gas that the jet, which will be formed right here, will have to push through. The ceiling will also be highly conductive, just like the plasma is in space. So if we wait for n rotations of the sphere, then the initially vertical field line will develop n loops, 1 loop per each rotation. Because now we have loops, this means that we have toroidal field, and there is pressure given in CGS units by the formula b squared over 8 pi. What matters is that the pressure is proportional to the square of the toroidal magnetic field, or to the square of the number of rotations that happened of the central object. So if we wait for longer and longer, the toroidal field will become stronger and stronger. And eventually the pressure that builds up basically we're twisting a magnetic spring, and of course it wants to push up, it will eventually drill a hole through the ambient medium and expand under its own pressure. So the jets is nothing but a magnetic spring twisted by the rotation of the black hole that expand under their own pressure. And if there is a piece of gas attached to the spring, it will be picked up and accelerated by the jets. That's how jets work. And the spring, of course, carries the electromagnetic and kinetic energy with it as it expands and accelerates, and then eventually slams into the ambient medium, transferring the rotational energy of the black hole, which was used up in twisting the spring, and depositing it into the ambient medium. So these jets then move away from the center of the galaxy, from the black hole over here, and accelerate. And we can watch them move really fast in the sky. So this is a bunch of frames from 1994 to 1998, taken 1 year apart. And you can see that there are features moving away from the center. And if we line them all up and draw a straight line for them, from the slope of this line, we can measure how fast it moves in the sky. And we find that the speed of motion is actually superluminal. It's about 6 times the speed of light, which actually tells us not that the special relativity of Einstein is incorrect. What this tells us is actually that the emitter, the blobs that forming part of the jet, are moving very close to the speed of light. So they're catching up with their own radiation, and that makes it appear in the sky as if the blobs move at superluminal velocities. In fact, these numbers give us the lower limit on the Lorentz factor of the intrinsic motion. So we know that the Lorentz factor of these jets has to be at least 6, which is pretty high. This corresponds to the speed of the intrinsic motion of 99-ish% of the speed of light. We can also look at the shape of this jet. So this is the cross-sectional radius, and this is the distance along the jets away from the black hole. So this one, both of them are measured in the gravitational, actually in Schwarzschild radii of the black hole. So this one goes from 1 to 10 to the 6 Schwarzschild radii, and this one goes from 1 to 10 to the 8 Schwarzschild radii. And between 1 and 10 to the 6 Schwarzschild radii, you see that the shape of the jet is a single power law. Z, the distance along the jet, scales as R, the cross-sectional radius of the jet, to the power of 1.7. So it's a parabola-like structure over almost 6 orders of magnitude. And then after that, the jet seems to open up and become conical. So how does nature manage to produce jets that accelerate to relativistic Lorentz factors and maintain this consistent, beautiful, single power law-like shape? So let me try and address this question. But before I do that, I want to kind of lay down the the landscape of the physical processes that I'm going to be looking at in order to understand what is the important ingredient or ingredients for jet production. So on the vertical axis of my 2D playground space, I will be plotting the thickness of the accretion disk. Thick disks above and thin disks below. These ones are typically non-radiative. That's why they're puffy and thick. They don't really emit much light, and therefore they don't lose much energy in radiation. These ones are luminous. These are bright disks, and that's why they are geometrically thick. And the other axis here along the horizontal direction will signify the strength of the magnetic field. Weak vertical field towards the left side and strong vertical magnetic field to the right side. So this part here has thick disks with lots of vertical magnetic field, which is, we know, very conducive to the jet formation. So I'm going to start with this, and I'm going to try and fill out the rest of the space as time allows. And we will see a lot of interesting surprises along the way. So here's an example of a thick disk. This is a disk threaded with vertical magnetic field. Disk is shown in blue, jets are shown in reddish purple. And we will now zoom out by about 3 orders of magnitude to show you the scale separation that we are able to achieve nowadays in 3D when we simulate black hole accretion. This is work done by Kosha Chatterjee, whom I commented at the University of Amsterdam when he was a grad student there. And now he is a Black Hole Initiative fellow at Harvard. So this is not surprising. A black hole plus a accretion disk equals jets plus outflows that collimate these jets. But what's important here is we were able to achieve 3 orders of scale separation between the black hole and the ambient medium. But remember, the jets maintain parabolic-like structure for over 5 orders of magnitude. And that's what Koshik has been able to do, albeit in 2 dimensions in axisymmetry. This is the analog picture of the shape of the jet. So this is the jet cross-sectional radius, and that's the distance along the jet. And you can see that the observational data points shown in various blue data points, they very well agree with the red line, which shows the simulation results. So without any fine-tuning, the first simulation that we ran that had a long-term jet that propagated outwards for about 5 orders of magnitude agreed perfectly with the shape of the jet that we observe in M87. Moreover, not just that, but also if we plot the Lorentz factor, which is this wiggly purple line, and compare it to this broken power law shape inferred from the observations, the two are qualitatively invariant with each other. So this suggests that we now finally understand where does the collimation of these jets come from and where does the acceleration come from. There is, of course, a lot of analytic theory that I won't have a chance to talk about. We understand why the Lorentz factor is what it is, but there are really interesting things like the Lorentz factor sometimes goes down and sometimes goes up, which is happening due to the mixing between the jets and the ambient medium. The corollary of this is if we leave the black hole alone with a thick disk with lots of vertical magnetic field, jets will emerge and they will be healthy and they will match the observation that we see in some of the most enigmatic systems, such as the M87. How about this case? In this case, we will remove the vertical magnetic flux. That's the flux, that's the magnetic field that was necessary for the production of the jets, right? If we don't have a vertical magnetic field, how will the black hole be able to wrap it around and turn it into a magnetic spring? Certainly in this case, there will be no jets. Well, let's try and play around with this. So we will start with a rapidly spinning black hole. I want to give the jets the biggest chance possible, but I will take away the thing that they really need, the vertical magnetic flux. And the disk will be thick. So we will leave everything else the most favorable for jets, except the magnetic flux. We'll switch off things one by one. So this is a zoom in of about 100 times 100 gravitational radii on the side, vertical slice through the black hole, rotational axis, and the rotational axis of the disk. A red shows high density, blue shows low density, and this is logarithmic scale going from 10 to the minus 8 to 10 to the 2. So 10 orders of magnitude in density. So this is nothing, and this is everything. And this is a zoom out of about 1,000 times 1,000 gravitational radii on the side. So let's try and press play and see what happens. So the first thing you will see is that although we didn't have magnetic field lines in this plane, they will emerge. So these are magnetic field lines that are in the vertical plane where there were none. And the reason for this is that the accretion disk manages to create vertical magnetic field from toroidal magnetic field. This is the first time that such a large scale magnetic field production was seen from toroidal to vertical. And in fact, the magnetic field becomes so strong that it manages to produce a pair of powerful jets. And if we wait for longer and longer and longer, the power of the jets becomes comparable to the accretion power. If I plot mass accretion rate, accretion power in units of accretion power, jet power in units of accretion power, and magnetic flux, let's just focus on this panel, which is the dimensionless jet power. We will see that eventually it becomes larger than 100%, and this is time along the horizontal axis, which means that the jets are as powerful as the accretion, which is a telltale sign of dynamically important magnetic fields that can push the disk around. Indeed, you will see, if we have the time to get to that part of the movie, that the inner part of the disk becomes really shaken up and torn up by the magnetic fields. So in this case, we see that the jets approach the sort of magnetic saturation, or what we call MAD state, magnetically arrested disk state, where the jet power is comparable to the accretion power. Although, and this is as strong as the jet can possibly be, so magnetic field is as strong as possible, although we started with no vertical magnetic field at all. So this means the jets are really resilient. Even if you take away the one thing that they need, the vertical magnetic flux, then they still manage to somehow produce it on their own. And this is a big issue. How do jets manage to form? Where does the vertical magnetic flux come from? And this is the work that is spearheaded by former undergraduate student Freddie Pardo at Northwestern. He now moved on to the University of Illinois Urbana-Champaign, and by the master's student Audrey Fon, who now moved on to do her PhD at Queen's University in Canada. So what we're finding is that we're finding some indications that what we're seeing here is the work of alpha omega dynamo. Although this is not completely certain, this is whole thing is very messy, it's turbulent, and so we're doing our best to try and figure out the correlations that will tell us about the nature of the dynamo here. What about these results depending on the numerics? I mean, you will say, why didn't people see that dynamo before? Maybe we went to high enough resolution to see it. Yes, the resolution here was one of the highest resolution to date, 2000 times 600 times about 1000 cells in R, theta, and phi direction. Typical resolutions are about maybe 5 times less, maybe 10 times less in every direction. So the simulation might have had, 1,000 times many more cells than the typical state-of-the-art simulation in the field. But what if we went to even higher resolution? Would things change? And this is a very important issue. So we'd like to understand the numerical convergence of our results with the resolution. And this is an example of the highest resolution simulation of black hole accretion disk ever, with about 5,000, 2,500 times 2,500 cells. You can see intricate detail that I will zoom on in here. And in particular, I will highlight these features, these blobby features that emerge into this accretion disk that is squeezed from both sides by the very strong magnetic flux. These are telltale signs of plasmoids that mediate the reconnection between the oppositely directed magnetic field lines that are squeezing the accretion disk from both directions. This work is led by Bart Ripperda, who is a postdoctoral fellow at Princeton and the CCA. The paper was just recently posted on arXiv. Check it out. The movies are beautiful and the physics is spectacular. The fact that these blobs appear here might not seem like a big deal, but it is, because once reconnection goes into plasmoid dominated regime, which only happens at high enough resolutions, then no matter how much higher resolution you take, the speed of reconnection will not change, which means we finally have resolved reconnection, at least in the large scale current sheet in the magnetosphere of a black hole, which opens up the possibility for us going to even higher resolutions and resolving the current sheet reconnection inside of the accretion disk, which is something that we will do in the future. And this brings us closer to finally resolving the turbulence in the accretion disks in a way that will not depend on resolution at all. So this is all perfect, but also makes me a little bit sad because I wanted to try and find a way of shutting the jets down, and they managed to survive. And we know that only about 10% of the jets, only about 10% of active galactic nuclei actually produce jets. So what about 90% of them? So they're not here, they're not here. What about trying to make the disk thin and see what we get? But before that, let me first try something else. Let me tilt the system and see if that might help us to shut up the jets. So I'm going to come here, which is the easiest way to make the jets, but for the tilted system, and we will see what happens. And I will try and wrap up in the next 10 minutes. So this is this favorite galaxy of mine that produces the feedback. But here you see there is not many symmetries in the system. The jets are pointing in sort of various directions. There are the kinks in the jets. They're not really looking like they are going along a straight line. Whereas in the simulations, what we typically do, we put in an accretion disk in the equatorial plane, and we let the jets emerge perpendicular to it. And it's the same plane as the plane of the black hole. However, more likely is this scenario. As I mentioned at the very beginning, the gas comes from large distances. It has no idea which way the black hole is spinning. And so a typical misalignment angle between the black hole midplane and the disk midplane is about 60 degrees. Will the system reorient like this and send the jets perpendicular to the disk, or will it continue sending the jets perpendicular to the black hole midplane, or will the jets be even there in the first place? So let's try and address these important issues. I'm going to skip this sort of theory slide, and I'm going to show you a bit of a flavor of what sort of numerical scheme we use in order to address all those questions. You saw that we were able to achieve resolutions which were unprecedented. And the way we were able to do that, actually, it's twofold. One is we have an amazing team of graduate students, former graduate students, now postdocs, and undergraduate students. For instance, Valeria is running a linear wave test to make sure that things are all working out. Matthew and Koshik developed the code itself that has adaptive meshes, and allows us to focus the resolution where we need it. But also what's really important is that this is the only production general relativistic magnetohydrodynamic code that can run on graphics cards, on many of them, on thousands and thousands of them. This gives us huge amount of speed up. In addition to adaptive meshes and adaptive time stepping giving us another speed up. If we add up all the speed ups, we get that we can solve problems, we can attack problems which are about 1,000 times more complex than what our team was able to attack before we moved on to GPUs and added all of these advanced features to the code. Which means that coupled with huge GPU accelerated resources, we can do a lot of cool things. That is partially what's driving our science. So here is an example of what we can do. If we take a disk that's tilted by 45 degrees to the equatorial plane of the black hole, it's pretty thick. It's an aspect ratio of 10%, thickness divided by distance of 0.1. And the black hole spin, which is vertical in this figure, is 93% of the maximum. So let's take a look at what happens here. So the jets are shown in red. The disk is shown in blue. I don't know if you can see it well, but the disk is spinning around, kind of precessing because the black hole drags the space-time around and the tilted disk rotates together with the space-time. And this disk taking the jets with it. So this is the first demonstration that A, tilted disks that are precessing can produce jets, and B, that the jets actually follow the direction of the disk and precess together with the disk. So if you see the disk that's actually precessing like crazy, then you can also infer the presence of the spin of the black hole and maybe potentially measure the black hole spin. I just realized that my video actually was pretty bright. I don't know if it was hard to see. So I just corrected that. Hopefully it will be better. Okay, so that's cool. What happens if we tilt the black hole by 90 degrees? Something really dramatic happens. We're still trying to understand this. The first indications, and this is work led by Kaushik Chatterjee, is that the black hole is not able to hold onto all of its magnetic flux when it's tilted. It seems like MADS, or dynamically important magnetic field, doesn't emerge in this case. We're still trying to work it out. Would love to talk to Jean-Pierre and all the other theorists and observers in the room to try and figure out if this has interesting theoretical and observational manifestations. You can also make images of tilted and aligned disks, compare them to the observations. And what we find is that tilted disk here versus the aligned disk, it seems to maybe fit the data a little bit better because the tilt causes the peak of the emission to shift a little bit to the left, signs of which we might be seen in the observations. This opens up the possibility that the images of the black holes can reveal something about not only the black hole spin and mass, but also the tilt of the accretion disk. And I'm now in the finishing line. I'm going to go down to thinner disks and ask, can the tilt and thinness of the disks finally shut the jets down? A spoiler alert, yes. Okay, so let's try and get there step by step. So let's tilt a disk relative to the black hole by 45 degrees, and let's make it even thinner. This disk is 3 times as thin as the previous one that was precessing, and it's 10 times as thin as the thick disk that we considered before. So this is a rather thin disk. In fact, at the time we published this paper, this was the thinnest disk ever. You will ask me, why do you want a disk that thin? Well, because luminous disks in galaxies, in quasars that are luminous, they actually are even thinner than this. They can be 0.01 or even less in thickness. So we actually are still not quite there, the realistic values of this thickness. So let's run the simulation and see what happens. So this is a zoom in of about 30 times 30 gravitational radii on the side. And this is a zoom out of about 200 times 200 gravitational radii on the side. The black hole plane is horizontal and the disk plane was tilted like this, but then the disk precessed and now it's like that. And what's really spectacular is that the central regions of the accretion disk spontaneously align with the black hole midplane. This effect was long sought. It's referred to as Bardeen-Peterson effect. And for 45 years, no sign of this effect emerged in a general relativistic magnetized simulation. This is the first demonstration of this effect. This is a huge deal. It affects how black hole spins evolve in galaxies, how the black hole feedback appears, and lots of others. And emission, of course, of the central regions. So I'm not going to be going into there. We're exploring all of these effects right now as we speak, and we're getting some really cool results. What happens if we tilt the disk even more by 65 degrees instead of 45 degrees? We get something like this in the vertical slice. That looks weird. In 3D, this is how it appears. The disk is tilted at 65 degrees in this case, but now there is not one disk midplane, there are two disk midplanes. The inner disk was dragged around by the frame dragging of the black hole to the point that it became too lazy to drag this entire large disk on its back and decided to tear off the outer disk. Let's see how this works in the movie. So initially, the disk is tilted by 65 degrees like this. The equatorial plane of the black hole is like that. And you can see that the jet's coming out perpendicular to the disk. But now the inner parts of the disk, they tear off the outer disk being dragged by the black hole at small radii. The inner disk takes the jets with it. These jets slam into the outer disk over here, and they completely splatter around, which will lead to spectacular observational manifestations. In fact, the jets completely blow away the outer disk, so it's no longer there. See, it used to be blue, now it's greenish, so the density dropped substantially. The disk continues tearing down to smaller and smaller radii. The jets escape along the path of least resistance, and we expect a lot of interesting time variability here as the disk passes in front of the line of sight, obstructs the emission from the central engine. So there will be high energy emission from the jets slamming into disks. Lots of exciting things that I will not have to talk about in this talk. But also we haven't yet added radiation to our code, which we currently have just done. And the new simulations right now include the radiation. They are running as we speak on the Summit supercomputer, which is the largest supercomputer in the US currently that's powered by graphics cards. So far, we have been completely unsuccessful at shutting down the jets. In all of these cases, the jets were there. Let's go to our case of last resort, to the case when the disk is geometrically thin and doesn't have any vertical magnetic flux. So it's this one. This is the most expensive simulation in GRMHD ever, with effective resolution of about 14,000 times 5,000 times 8,000. All that resolution is focused in this disk using adaptive meshes. The disk is tilted by 70 degrees relative to the equatorial plane. This is the thinnest disk with aspect ratio of 1/50th or 0.02, so it's a bit thinner than the previous ones that you saw. And what's most important is that magnetic field is purely azimuthal. There is no magnetic field that's perpendicular to the disk midplane, which means that perhaps in this case, finally, the black hole will not get the flux of the orientation it needs, and it won't be able to produce the jet. Let's see if that indeed happens finally for these thin disks. So you see that the black hole frame dragging causes the disk to warp. You can think of the disk as being a membrane where you torque the inner part of the membrane, and so it warps to resist the torque. And the black hole peels off the inner parts of the accretion disk, causes them to be torn off and consumes them. And that happens periodically, which actually will be very nice for producing quasi-periodic signals from black holes. And in fact, there is a paper in preparation that's analyzing specifically that. You can see one of these tearing events happening right now. And if we wait for longer time, and I can try and skip to that point, we will find that this inner accretion disk, maybe it's happening right now, it will form an aligned part at the center. So we find that all of the effects that we were really excited about in the presence of vertical magnetic fields, such as the Borden-Peterson alignment of the disk, that is what you're seeing right now in complete absence of jets or large-scale magnetic flux. In fact, you see something that doesn't look like a disk at all. You see that there are multiple planes of the disk. There is stuff that's trying to go around. It's a really complex structure that is not a flat pancake surrounding the black hole, which calls for reevaluation of what we think of accretion disks. They are not as simple as we thought. Let me wrap this up. This is the complex grid that we use. You can see that the resolution focuses on the disk midplane, which is really, really thin. And it is the adaptive meshes that make this simulation possible. Since I'm running out of time, I will skip a few things on black hole feedback in various systems, radiation implementation of the code, and resistivity. And I'm going to go to summary, where we discovered, to our astonishment, that the jets are extremely resilient. No matter what sort of fields you give them, vertical field or horizontal azimuthal fields, both of them produce very strong jets. However, the jets can disappear for thin disks without vertical field. That's the only context where we found that the disk accretion around the black hole wasn't able to produce a relativistic jet. Typical tilted black hole systems have a lot of exciting stuff going on. The inner parts of the disk can align with the black hole midplane. The disk can break and tear into several subdisks, and this disk can interact with the jets, with each other, and produce a bunch of poorly explored observational manifestations, transients. And that's something that we are hard at work at exploring. If we go to really insane resolutions, we can finally achieve, we think, convergence, at least in large-scale properties of current sheets around the black holes. And in the future, we hope to achieve full convergence in full 3 dimensions at resolutions which exceed the resolutions of local shearing boxes. So we will be in a really good globally converged regime. And by the addition of radiation and the resistivity, nuclear physics, we hope to push the understanding of various transit systems on various scales to completely new levels. Thank you so much for your attention, and sorry for slightly running over.
Okay, thank you, Sasha. Are there any questions? I think there are several hands. So, Ilake, please.
Hi, Sasha, can you hear me?
Yeah, I can hear very well, loud and clear.
Thank you very much for the great talk. So at the very beginning, when you showed the EHT pictures, you mentioned that due to the double boosting, we have like this clockwise motion of the material around the
I think a leg got cut off.
Okay, so maybe we till you reconnect, so we can take the other one in the list. So Joe.
I don't think we hear
Your microphone
you,
is
Joe.
not turned on, Joe. You're still off. You're muted.
It doesn't show like muted. I think it's maybe you want to pick a different microphone if you have multiple. Like there is a little up arrow right next to the microphone. If you click it, you will pick a different one.
How about that? Is that better? Can you hear?
Yeah, we can hear you now. Yeah. Mm-hmm.
Okay, thanks for a great talk. I have it's probably a very naive question. What is the jet made of? You didn't say anything about that, really.
Yeah, thank you so much for the great question. So the jet is primarily made out of electromagnetic field with electron-positron plasma on top of that, and some baryons like protons primarily. So this is the main content of the jet. Where the protons come from, we don't quite know. Where electron-positron plasma comes from, we think it's the sort of the plasma discharge in the vacuum gaps near the black hole. For low mass accretion rates and for high mass accretion rates, it could be the annihilation of gamma collisions that create the electron-positron pair. So this is what we think we understand. Where the baryons are coming from, it's a bigger question. It's very hard to get the baryons across the magnetic field lines. So it's probably some sort of mixing instability at the interface between the jet and the ambient medium. And we see such instabilities in axisymmetric simulations. So we are now analyzing more of the results in 3D to try and see if those results carry over to 3 dimensions, where hopefully we can mix in the gas from the sides into the body of the jet. That would be really cool if we actually see that in 3D as well.
So what can you say about the ratio of hadronic pairs to lepton pairs? I mean, do you have any feeling for what that might be?
Yeah, so just pure number-wise, there will be many more electron-positron pairs than baryons. In terms of mass, the baryons will win single-handedly. So if we didn't have any baryons in the jets, then the maximum Lorentz factor that the jets could get is like, it's huge. It's like 10 to the 13 or something like this. It's ridiculous. And we never see such high Lorentz factors. In principle, they wouldn't be able to be achieved because there are some geometrical constraints on how fast the jets can go. But in active galactic nuclei, for instance, we would expect that Lorentz factors which are of order of the inverse open angle, and we find Lorentz factors which are about 10 times smaller than that. So that suggests to us that there is actually a limitation on the there is enough gas on the jets to slow the jets down from accelerating up to the max possible Lorentz factor. And why and where that level of jet contamination with baryons comes from is completely open question. What's confounding for me in particular is that in different systems, this limitation Lorentz factor is different. In gamma ray bursts, the limitation seems to be maybe 1,000 for Lorentz factor. In FT galactic nuclei, maybe tens to a few tens, like 10 to 30 is the typical value of Lorentz factor. And in black hole binaries and X-ray binaries, stellar mass black holes accreting from a stellar companion, the limit seems to be just a few. So the mass scale and the accretion scale seem to affect substantially the amount of baryons that infect the jet. And why and how that difference emerges is a completely open issue. I don't know the answer to that.
Okay, thank you.
Sure thing.
So Felix, please.
Quick comment. Well, in the case you mentioned stellar mass black holes, the jets, in the case of stellar mass black holes, the most powerful jets come from sources like SS433, GRS 1915, which are the sources that have accretion disk with very high column densities. And the same happens in the highest quasars at redshifts in between 5 and 7, where the column densities in these quasars observed with ALMA are larger in more than 50% of the cases, larger than 10 to the 4 atoms per square centimeter. So the gas column densities around accreting black holes must be an essential ingredient to produce very powerful jets. I would like to know your, besides magnetic fields, I would like to hear your comment on these observations.
Yeah. So thank you very much for sharing that. I will use this as an excuse to show you some of the things that I ran out of time to show you, namely the interaction of the jets with the ambient medium. What causes the sort of differences in the jet morphology? So some jets, they seem to be doing just fine, and the other ones fall apart early on. So this one is, for instance, 70 kiloparsecs long. This is 5 kiloparsecs long. One part of the question is, why do we need this large column densities? And so the answer to that is large column densities means that there is a large absolute amount of stuff there, which means mass accretion rate, absolute value of it, it's high. So that means that the jets, whose power we think is roughly limited by the accretion power, can also be more powerful, right? So if you double the amount of mass that the black hole receives per unit time, then we will also double the power of the jets. Okay, so that's kind of intuitively okay. We can live with that. But the other thing that we also would like to understand is, how does the ability to produce jets relative to the accretion power varies as a function of that power? So these are low luminosity AGN, for instance, and they produce jets at a good fraction of accretion power. So both of these have jets whose power is roughly m.c squared. And we think that in SS433, probably, although not certainly, we have jets whose power is comparable to the accretion power. They seem to be highly super Eddington. In quasars, the jets are also roughly, m.c squared. So this actually is a pretty luminous system. I think it's maybe like 10-ish% of Eddington. So actually, I think I misspoke. So this was, I said, was low luminosity. No, this is a luminous system with a thin disk over there, we think. And it also produces powerful jets. Of course, these jets are 100 times more powerful than those. And in fact, it turns out to be the biggest distinguishing feature between the morphologies over here. So I can show you what I mean. So if we take a disk, immerse it into ambient medium and let it go, you see that the disk starts to develop this sort of shaking and it starts to break up. So this sort of instability is similar to what we see in the M87 jet, are coming from the fact that the jets are magnetic springs, and if we squeeze the spring, it can fly sideways. So this is sort of magnetic kink instability that limits the jet ability to propagate. You can see the same sort of effects. Unfortunately, I forgot to replace this movie with a 3D one, but in the case of collapsers, the recent work that Or just posted online shows how we can follow the jet from the center of the star outside, and where the jet undergoes various instabilities inside of the star, which are rather similar to that. So the bottom line is, in order to have a jet that is powerful, stable, we need to have two things. A, we need to have a large magnetic field at the center, which allows us to produce jets of power comparable to accretion power. And what you were asking about, how can we have absolutely powerful jets, like in actual ergs per second? Well, for that, we need to crank up the whole thing by increasing the units of mass accretion rate. So if we bring the accretion rate to the highest possible ones, like in collapsars or in luminous galaxies, where the actual numbers of like grams per second are huge, that's when we will get the most powerful jets ever. Like you said, JRS 1915, or in the AGN. I hope that I answered your question.
Thank you very much.
So we'll take the question by Ilek, please.
Sorry for the unfortunate disconnect in the middle of the question. So yeah, like the question was about whether the flow, whether we can constrain whether we are dealing with a prograde or retrograde flow if we neglect like the tilt question. If we have like this counterclockwise motion, and we assume that the jet is in the direction of the spin axis, can we know whether like the disk and black hole spin are aligned or counter-aligned based on the radial extent of the ring, for instance?
Yeah, it's very hard to tell anything about the spin of the black hole, apart from the fact that retrograde spins are ruled out. So that actually we can tell that it has to be a positive spin, spinning the same sense as the disk. Sorry, yeah, black hole spinning the same sense as the disk, and it has to be of order unity. What that means is a little bit of an open question. Typically the EHT papers, and I'm covering the whole picture. Typically the EHT papers, they claim that the spin needs to be greater than about 1/2, so greater than 0.5. This comes mostly from energetic arguments. Just like Felix was asking, how do I get the most energetic and powerful jet? And the jet in M87 seems to have roughly the same power as accretion. So P jet is equal to m dot c squared. If the spin is lower, then the jet power will be lower. Jet power, you can think of it as spin squared times m dot c squared, roughly. And so if the spin is like 0, then there will be no jet. If the spin is 0.1, then the jet will be like 1% of accretion power. And so if you want the two to be comparable to each other, you basically are forced to conclude that, okay, the spin is probably of order unity, maybe like 1/2 of or above. So that way we're within a factor of few jet power in jet power in comparison to the accretion rate. So yes, the answer to your question is that we think it's a prograde system, but how much higher the spin is compared to 1/2, we don't know. It could be 1/2, it could be 0.999 for all we know.
But the power of the jet depends both on the spin and of the magnetic field, right?
That's right, yeah.
So like the magnetic field measure we have in the vicinity, is it like a well-constrained quantity compared to what we have in the jet? Like, do we know exactly where the magnetic field is measured?
Not super well. I mean, we know by order of magnitude that the magnetic field is a few hundred Gauss, actually similar to Sagittarius A star. But bigger black holes, well, I won't go into the details, but what I think is most constraining is that basically both the spin and the magnetic field strength, they are pushed towards the maximum possible values, because the jet power, for it to be comparable to the accretion power, theoretically, we know that it's very close to the magnetic field saturation limit when the black hole is at the maximum possible magnetic flux in this sort of magnetically arrested disk state. So that's the primary reason why we think that both the magnetic flux or the magnetic field strength and the spin have to be at their max values. And so we think naturally that if we're halfway to mad, we're probably all the way to mad, because it's unlikely that the magnetic field was tweaked by nature to be just below the limit. We know if we give it more, it will flood the black hole all the way to capacity, and we will produce the jets that are maximum power for a given spin. So that's why we think that the black hole field strength is at the mad level, the maximum level. And magnetic spin wise, that's where we don't quite know. Will the nature, the accretion history, provide the black hole, leave us the black hole with the maximum spin, or not quite? Most of the accretion tends to spin up the black hole, but actually magnetic arrested accretion tends to spin it down. That's a paper that a graduate student and I are preparing. And so depending on the fraction of time that the black hole accretes in the mad state versus the time that accretes in the non-mad state, where actually the black hole spin goes up in non-mad state, and in mad state it will go down. So depending on the durations of both of these phases of accretion, the spin can either go up to maximum spin or go down all the way almost to zero. And so here it seems like it's very close to 1. If I were to make my bets, I would say that the spin of black hole in M87 is like 0.9 and above.
Okay, thank you very much.
Sure thing.
We got 2 more questions. Paramvir, please.
Yeah, hi. So my question is, assuming that you have 2 scenarios, in one case you have a very weakly magnetized jet, and in other case you have a really highly magnetized jet, and in these 2 cases, what would be the effect on the jet structure and some recollimation shocks?
Thank you for the question, Paramvir. So in all of these cases that I showed you, in all of the simulations that you saw over here, the jets were highly magnetized. The reason for this is observations are telling us, okay, they were highly magnetized at the base, okay?
Okay.
So are you asking about the base or at large distances?
Well, we can start from the base and then...
okay,
yeah.
Fair enough. Okay, so because in our case, the magnetic energy is the only energy that can basically be converted in all the other forms of energy, and this is basically the fuel that that launches the jet and powers it. We have to have the jets at the base be dominated by the magnetic energy. So you can think of the jets as converting magnetic energy into all the other forms of energy. Kinetic and thermal energy, and energy of non-thermal particles. So if we want the jets to reach Lorentz factors of, let's say, 10, for instance, then it means that whatever mass the jet has needs to be coupled with energy that exceeds the rest mass by a factor of 10, right? E is equal to mc squared. So if something is moving, then this formula becomes E is equal to gamma mc squared. And E in this case is the magnetic energy coupled to mass m. And so that means that the magnetic energy, E, has to exceed mc squared by a factor of gamma, the Lorentz factor that eventually the jet has accelerated to. So if we see a jet like in M87 moving at gamma of 6 or above, that means that magnetic energy needs to dominate rest mass energy at the base of a jet by at least a factor of 6. In fact, in practice, the jets never accelerate to the maximum Lorentz factor. They stop at around a factor of 1/2. And so you need to have maybe a factor of 10 dominance of magnetic energy over rest mass, at least for the case of M87. And for all the other sources, if you know what Lorentz factor is, multiply that by a factor of 2, that's the dominance of magnetic energy at the base that you require in order for the jet to be able to reach that. Now, depending on the distance, the magnetization can change. Of course, we start at, let's say, a magnetization of 10 near the black hole. And let me show you, let's say, a plot. I don't have a plot of magnetization here. It's in the paper by Bakoshek. But think of a magnetization as basically roughly maximum Lorentz factor, which is 10 in this case, divided by the current Lorentz factor, and subtract 1 off. So that's the Lorentz factor here. It starts at basically of order unity over here and goes to roughly 6-ish or so far away. So magnetization will start over here at around, in our case, it actually starts at around maybe like 50. And it goes up here to around, let's see. No, sorry, I apologize. No, we start around 10 over here. and we end up at around like 1.5 to 1, something like this. So that's how we go from Lorentz factor of around 1 to around 6. So something like this is what we have in this model. Is there a way to get jets to be much less magnetized than that? Yes, there is a way, and the recent work by Orr, whose movie I unfortunately don't have right now, and I don't think we'll be able to show it to you effectively, but the 2D version of this movie, the axisymmetric version of this movie, is kind of here. And so in the case of collapsing stars, or in any other case when the jet has to navigate an ambient medium. So for instance, in the case of active galactic nuclei, what the jets do, they go out like this until they hit the ambient medium, then they recollimate because they need to drill a hole, and it's much more effective for them to pinch so that they focus all their energy in a small area. And then they bounce back. And then after that, they become mostly cylindrical if the ambient medium is still present outside. So in this sort of pinching region, as we call it, recollimation region, the jets become very compact in their cross-section, and they also slow down, both of which are devastating for jets. Is if the jet moves very fast, there is no time for instabilities to grow. And if it slows down, there is more time, because the proper time slows down when the jet is relativistic. When it slows down, proper time goes faster. So it means that the instabilities that grow in the proper time in the comoving frame of the jet, they have the time to develop. Instabilities grow on the time scale that it takes for Alvin waves, or the magnetic analog of sound waves, to go around the jet a few times. And if the jet pinches, then suddenly that time scale becomes much shorter, which means that the instabilities can grow faster due to multiple reasons. And so what we find indeed that the jets at this pinching point, they can twist on top of themselves and dissipate most of their magnetic energy into heat. So the jets that come out of the star can actually be really, really hot because of that dissipation, and basically unmagnetized. Like, well, not entirely, but their magnetization, at least in this simulation that Orr has just posted, is about 1%. Not 1 as we typically thought, but just 1% is carried by magnetic energy. Everything else is kinetic plus thermal. So something similar can happen in AGN. This is what we think happens in gamma ray bursts. And this is really important because if we have a lot of energy in thermal form, then that energy can be emitted through photospheric emission. And that's maybe what we see, the emission that we see in gamma ray bursts and gamma rays. Okay. Does that answer your question?
Yeah. Because it has a connection with the magnetization and of course the ambient medium. So yeah.
Absolutely. Ambient medium is very important for causing the jets to dissipate magnetic energy into non-thermal energy of particles. Yes, and so but that's what we think might be causing emission in M87 and HST1, where we think it's the point of interaction of the jet with the ambient medium. That's where we think maybe the stationary features that don't move, that are pinned down, they can come from the interactions with the ambient medium.
Okay, thank you.
Anytime.
So we had one last question, but Jean-Pierre do you want to still ask that question?
Okay, I'm sorry. It's very late. I just want to thank Sasha for his beautiful talk and advertisement, of course. And I wanted to ask just a short question, and the answer also, please be short. Do you apply these beautiful ideas to neutron star and maybe wide dwarf, especially magnetic and non-magnetic neutron stars?
Jean-Pierre,
thank you.
Thank you so much for asking this. Thank you for being the proponent and advocate of neutron stars and white dwarfs and all the other species of compact objects that have the surface. I am with you. I'm a big fan of those. And those are much harder than the black holes that don't have a surface, because surface means you need to be very careful at crafting the boundary condition, and boundary conditions is the hardest thing ever. So in the black hole, boundary condition is easy. We hide them behind the event horizon and we don't care about it anymore. We don't worry about it. Okay, we care about it as long as it doesn't bother us. With neutron stars, you have to treat the surface. You have to make sure that the magnetic field lines which belong to the neutron star behave well. And that's another parameter, the magnetic field that the neutron star possesses. Black hole doesn't have its own magnetic field. It's brought in from the ambient medium. That makes the problem harder, but also much more exciting. And as you say, there's not just neutron stars, there are also white dwarfs, which is a really important system with a smaller dynamical range. The disks are smaller in size compared to the surface radius of the white dwarf, which makes the systems really exciting to study. And so the good news is that now we have a team of about 3 to 4 postdocs, depending on maybe even more, because everybody starts to realize this is a really important system to study. And so we hope to make really rapid progress there. We in fact have some really cool simulations where we have looked at the differences in terms of the outflows, depending on the polarity of the supplied magnetic field relative to the polarity of the magnetic field that the neutron star possesses. And we found that the results can be very different, or they can be very similar, depending on how close the system is to co-rotation. Near co-rotation, there is no difference with up and down magnetic field geometries. Far away from co-rotation, you can either shut down the jet or launch a jet, depending on whether the magnetic field that we supply can reconnect with the closed zone or not. So there is a lot of excitement there. And soon we hope to add radiation treatment to the accretion neutron star problem. So stay tuned, and by all means, we'll be very happy to chat science about this and explore what sort of questions we can try and attack. So lots of new things coming up. Please stay tuned.
Большое спасибо.
Пожалуйста.
Okay, so let me stop the recording.